welcome to this problem walkthrough. Today, we'll tackle a popular string manipulation problem from LeetCode, problem number 520, detect capital. This challenge is great for practicing string validation techniques and learning how to handle different cases efficiently. Let's dive in. In this problem, we are tasked with determining whether the capitalization of a given word is correct based on specific rules. A word is considered to have correct capitalization if it satisfies one of three conditions. First, all the letters in the word must be uppercase, like in the example USA. Second, all the letters must be lowercase, such as in the word LeetCode. Third, only the first letter of the word is uppercase, while the rest are lowercase, as in Google. If any of these conditions are met, we return true, and if none of them are satisfied, we return false. The input will be a single string consisting of only English letters, and the output will be a Boolean value indicating whether the capitalization is valid. Let's look at our first example to understand this problem better. Here, the input is the word USA. Since all the letters in the word are uppercase, it satisfies the first rule of correct capitalization. Therefore, the output for this input is true. Now, consider another example where the input is LeetCode. In this case, all the letters in the word are lowercase, which aligns with the second rule. As a result, the output is also true. Now, let's examine another example. This time, the input is Google. The word starts with an uppercase letter, and all the remaining letters are lowercase. This satisfies the third rule for correct capitalization, so the output here is true. On the other hand, consider the word flag. Here, the capitalization does not match any of the three valid patterns. The first letter is uppercase, but the remaining letters alternate between uppercase and lowercase, which violates all the rules. Therefore, the output in this case is false. Finally, let's review the constraints and edge cases to ensure we handle all scenarios effectively. The input string will consist only of English letters, and its length will range from 1 to 10,000 characters. Single character words, such as a or b, always satisfy at least one rule and should return true. However, words with mixed capitalization, like hello or world, that don't fit the three patterns must return false. Additionally, the solution should efficiently handle very long strings up to the maximum length of 10,000 characters. Note that empty strings are not valid inputs according to the constraints, so there's no need to account for them. To begin, let's consider the brute force approach, which involves validating the word's capitalization by examining each character individually. The idea here is to check whether the word satisfies one of the three conditions: all characters are uppercase, all characters are lowercase, or only the first character is uppercase. For implementation, we would iterate through the word and use methods like isupper or ilower on each character to verify its case. While this method is straightforward and easy to understand, it has some drawbacks. Specifically, it requires repeated checks for each condition, leading to redundancy. For longer strings, this can become inefficient. Although the time complexity for this approach is O(n) per condition, since we check three conditions, it totals to O(3n), which simplifies to O(n). On the positive side, this method has a constant space complexity of O(1), since no additional space is used beyond the input word. Now, a more efficient method is the optimized approach, which uses a single scan of the word to determine its capitalization pattern. The intuition here is to reduce redundancy by combining condition checks into one pass. For example, if the first letter is uppercase, we can verify the rest of the word to ensure that it's either fully uppercase or fully lowercase. On the other hand, if the first letter is lowercase, we simply check that all subsequent characters are also lowercase. This approach leverages Python's built-in methods like isupper and ilower, along with string slicing to simplify the implementation. The main advantage is its efficiency, as it avoids multiple scans of the string. However, it requires careful handling of edge cases, such as one-letter words. The time complexity remains O(n) due to the single scan, and space complexity is O(1). Another alternative is the regex approach, which uses patterns to directly match valid capitalization formats, such as all uppercase or first letter uppercase. While regex offers a compact solution, it can be slower for longer strings and is often harder to debug, making it less practical for this problem. The chosen strategy is the single scan with case checks, as it achieves an optimal balance between simplicity and efficiency. By performing only one scan of the word, it avoids redundant checks and eliminates the overhead associated with regex matching. With this approach, we use string slicing and built-in case-checking methods to directly evaluate the required conditions. A key observation is that the problem boils down to 3 clear patterns of capitalization, which makes it straightforward to implement this solution. Compared to the brute force approach, this method significantly reduces redundancy by consolidating the checks into a single pass. While regex is a viable alternative, it is less efficient in this case due to its computational overhead. Overall, this strategy provides a clean and efficient solution to the problem. In terms of complexity, the chosen approach is both time and space efficient. The time complexity is O(n), where n is the length of the word, as the entire string is scanned only once. The space complexity is O(1), since no additional data structures are required beyond the input itself. This makes the solution not only robust but also highly efficient, as it directly addresses the problem's requirements without introducing unnecessary complexity. By leveraging Python's built-in methods and focusing on the core patterns of capitalization, this approach ensures clarity and effectiveness in implementation. To solve the detect capital problem, we need to determine if a given word adheres to one of 3 specific capitalization rules. The first rule is that all characters in the word must be uppercase, such as USA. The second rule is that all characters must be lowercase, like LeetCode. Finally, the third rule allows only the first character to be uppercase, while the rest must be lowercase, as seen in Google. The algorithm begins by validating the input to ensure it's a valid string. If the input is invalid, such as being an empty string, the algorithm either returns an error or handles it appropriately. Next, we calculate the length of the string and store it in a variable, which avoids redundant calculations during the process. If the string has only one character, it automatically satisfies all 3 rules because a single character can be either uppercase or lowercase. For the first capitalization rule, we can use the isupper method on the entire string to check if all characters are uppercase. Alternatively, we can iterate through the string and verify that each character is uppercase, though the built-in method is more efficient. For the second capitalization rule, we check if all characters in the string are lowercase. This can be done using the ilower method on the entire string, which will return true if the condition is met. Alternatively, we could iterate through the string to confirm that each character is lowercase, though, again, the built-in method is more efficient. The third rule requires a bit more nuance. First, we check if the first character of the string is uppercase using the isupper method. Then, we use the ilower method on the substring starting from the second character to the end of the word. If the first character is uppercase and the remaining substring is lowercase, the word satisfies this rule. Once we've evaluated the word against these 3 rules, the algorithm returns true if any of the rules are satisfied. If none of the rules apply, the algorithm returns false, indicating that the word does not conform to any of the valid capitalization patterns. There are a few key insights that make this algorithm efficient and robust. First, leveraging Python's built-in methods like isupper and ilower minimizes the need for manual character-by-character checks, improving efficiency. Second, the algorithm benefits from short-circuiting, meaning that once a valid rule is found, it stops further checks and immediately returns true. This avoids unnecessary computations. It's also important to consider edge cases. For example, single-character strings are always valid because they can be either uppercase or lowercase. Words with mixed capitalization, such as Google, are invalid because they don't adhere to any of the 3 rules. Additionally, non-alphabetic strings like 123 or @$, are not valid words for this problem and should be handled accordingly. In terms of data structures, the algorithm works directly with the input string and outputs a Boolean value, so no additional data structures are required. This simplicity makes the algorithm both easy to implement and memory efficient. Analyzing the complexity of this algorithm, we find that the time complexity is O(n), where n is the length of the string. This is because the algorithm may need to scan the entire string to evaluate the capitalization rules. The space complexity is O(1), as no additional data structures are used, and all operations are performed directly on the input string. Let's look at some examples to solidify our understanding. For the word USA, the ISupper method returns true, satisfying the first rule. The output is true. For LeetCode, the ILower method returns true, satisfying the second rule. Again, the output is true. For Google, the first character is uppercase, and the substring ogle is lowercase, satisfying the third rule. The output here is also true. However, for Google, none of the rules are satisfied. The first rule fails because not all characters are uppercase. The second rule fails because not all characters are lowercase. For the third rule, while the first character is uppercase, the substring ogilu is not entirely lowercase. Thus, the output is false. These examples illustrate how the algorithm systematically checks each rule to determine the result. This code solves the detect capital problem by determining whether a given word follows one of three capitalization rules: all uppercase, all lowercase, or only the first letter is uppercase while the rest are lowercase. The detect capital use function takes a single input word, which is a string. The solution uses Python's built-in string methods to check the necessary conditions. 1. Word.isupper checks if all characters in the string are uppercase. If true, the word follows the rule for all uppercase and returns true. 2. Word.ilower checks if all characters in the string are lowercase. If true, the word follows the rule for all lowercase and returns true. 3. The condition word 0.isupper and word 1.ilower checks if the first character is uppercase and the remaining characters are lowercase. If true, the word follows the rule for capitalization where only the first letter is uppercase, and it returns true. 4. If none of the above conditions are satisfied, the function defaults to returning false. The implementation is concise and handles edge cases such as single-character strings and empty strings gracefully because the string methods isupper and ilower will return appropriate results for such inputs without causing errors. The solution has a time complexity of O(n), where n is the length of the input word, since each string method iterates through the word at most once. It also has a space complexity of O(1), as no additional data structures are used. This is the Java implementation of LeetCode problem number 520, detect capital. The logic mirrors the Python implementation, using Java-specific methods such as toUppercase, toLowercase, and substring to check the capitalization patterns. Key differences include explicit type declarations, Java's string class methods, and the use of char@, for checking specific characters. This solution ensures correctness and readability while adhering to Java conventions. To start, let's look at example 1 where the input string is USA. The first condition in the function checks if all the letters in the word are uppercase using the isupper method. Since USA is fully capitalized, word.isupper evaluates to true. Because this condition is satisfied, the function doesn't proceed to evaluate any other conditions and immediately returns true. So, the final output for this example is true. Now, in example 3, we have the input string Google. The function first checks if all the letters are uppercase using word.isupper. Since Google contains both uppercase and lowercase letters, this condition evaluates to false. Next, it checks whether all the letters are lowercase using word.ilower. This condition also evaluates to false because Google is not fully lowercase. Finally, the third condition checks whether only the first letter is uppercase and the rest are lowercase by combining two checks. Word 0.isupper ensures the first letter G is uppercase, which is true, and word 1.ilower verifies that the substring ogle is entirely lowercase, which is also true. Since both parts of this condition are satisfied, the function evaluates this condition as true and returns true. The final output for this example is true. Lastly, let's consider example 4 where the input string is flag. The function begins by checking if all the letters are uppercase using word.isupper. Since flag has mixed capitalization, this condition evaluates to false. Then, it checks if all the letters are lowercase using word.ilower. This condition also evaluates to false because flag is not fully lowercase. The third condition checks if only the first letter is uppercase and the rest are lowercase. Here, word 0.isupper confirms the first letter F is uppercase, which is true, but word 1.ilower checks the substring lag and finds that the last character G is uppercase, making this condition false. Since none of the conditions are satisfied, the function reaches the else block and returns false. The final output for this example is false. The time complexity of the solution is determined by the operations used to evaluate the string. First, the word.isupper function checks if all characters in the string are uppercase. Since it needs to inspect each character individually, it operates in O(n) time, where n is the length of the string. Similarly, the word.ilower function checks if all characters are lowercase, which also requires iterating through all n characters, making it O(n) as well. The third condition, word0.isupper and word1.ilower, involves two parts: checking if the first character is uppercase, which is an O(1) operation, and slicing the string from the second character onward, followed by checking if the sliced portion is lowercase. The slicing operation creates a new substring of length n1, and the ilower function iterates through this substring, resulting in O(n) time overall. Finally, the else case simply returns false, which is an O(1) operation and has negligible impact on the overall complexity. Since these conditions are evaluated sequentially, the worst-case time complexity remains O(n), as each operation is linear and no operation dominates beyond this bound. In terms of the best, average, and worst-case scenarios, the best case occurs when the first condition, word.isupper, evaluates to true. In this scenario, the function returns immediately after the first check, resulting in O(n) time complexity. For the average and worst cases, if multiple conditions need to be evaluated, the time complexity still remains O(n), as each condition involves linear iteration over the string. When considering space complexity, the memory usage is primarily determined by the slicing operation. The input string itself does not consume additional memory since it is passed as a parameter. Built-in methods like isupper and ilower operate in place without requiring extra space. However, the slicing operation word1 creates a new substring of size n1, which contributes to O(n) space usage in the worst case. As there are no additional temporary variables or data structures involved, the overall space complexity of the solution is O(n), dominated by the slicing operation. When comparing this solution to naive or brute force approaches, we find that while both achieve the same time complexity of O(n), the provided solution is more concise and leverages Python's built-in functions for improved readability and efficiency. A naive approach might involve manually iterating over the string to check capitalization rules, such as explicitly checking if all characters are uppercase or lowercase. This would still result in O(n) time complexity, as each character would need to be inspected. Similarly, checking if only the first character is uppercase and the rest are lowercase could involve iterating over the substring manually, also leading to O(n) time. However, the naive approach could be slightly more space efficient, with a space complexity of O(1), as it avoids creating new substrings through slicing. Mathematically, the dominant operation in the provided solution is the iteration over the string, whether through isupper, ilower, or slicing. Each of these methods runs in O(n) time, and since no nested operations or extra loops are involved, the overall complexity remains linear. The slicing operation contributes O(n) space, confirming that both time and space complexities align with the stated analysis. One of the most common mistakes when solving this problem is misunderstanding the problem statement itself. For instance, some developers may assume that the task of validating capitalization only applies to English alphabets and overlook cases where the input contains digits, special characters, or even mixed content. This misunderstanding can lead to incorrect outputs when edge cases are not handled properly. Another frequent oversight is failing to account for empty strings or single character strings. These edge cases, such as an empty string or a single letter, can cause runtime errors or incorrect results if not explicitly tested. Finally, some developers resort to using nested loops to check each character in the string. This approach, while functional, unnecessarily increases the time complexity compared to a single traversal with optimized logic, which is more efficient, especially for longer strings. Another error to watch out for is ignoring the power of built-in functions. For example, instead of using Python's isupper or ilower methods to check character cases, some developers attempt to manually write their own logic. This can introduce subtle bugs and make the code harder to understand. Additionally, it's important to ensure your solution covers all valid variations of capitalization, not just one specific pattern like all uppercase letters. For example, solutions that only handle all uppercase strings but miss cases like a capitalized first letter will fail in certain scenarios. By not addressing all the problem's requirements, your solution becomes incomplete. When tackling string-related problems in interviews, there are a few key insights to keep in mind. First, many of these problems, including this one, can be solved efficiently with a single traversal of the string. Recognizing underlying patterns that allow for O(n) solutions is a crucial skill. Also, it's important to explicitly clarify edge cases during an interview, such as empty strings, single character inputs, or strings with mixed characters. This shows that you're thorough and attentive to detail. Furthermore, be prepared to discuss trade-offs, such as when to use built-in functions for simplicity and readability versus writing custom implementations, which might be faster in certain languages. Lastly, even if a brute force solution works, make sure to propose a more optimal alternative, as interviewers often look for your ability to refine naive approaches. To strengthen your understanding of string validation problems, it's useful to explore related problems. For example, detect capital, which we're discussing, is the classic example of validating capitalization rules in a word. Another interesting problem is valid palindrome, where you focus on ignoring non-alphanumeric characters to determine if a string reads the same backward as forward. Check if the sentence's pangram challenges you to validate whether a string contains all letters of the alphabet. Lastly, longest substring without repeating characters introduces efficient character-by-character validation techniques to solve for unique substrings. Each of these problems builds on similar concepts and helps you develop a comprehensive skill set for handling string-related challenges. When solving string validation problems, there are alternative approaches you can consider. Using regular expressions, for instance, is a concise and powerful way to define capitalization rules. In Python, a pattern like $AZ$ can validate if a word starts with an uppercase letter followed by lowercase letters. However, regex can be harder to debug and may be less efficient for large inputs. Another approach is character-by-character validation, where you traverse the string and use functions like isupper or ilower to check each character. This method is straightforward and easy to read but may feel more verbose compared to regex. Finally, you could use ASCII values to manually check character ranges, such as 65 to 90 for uppercase letters. While this can be slightly faster, it's often less readable and more prone to errors. By weighing the trade-offs of these methods, you can choose the approach that best fits the problem's constraints and requirements. Great job! We've explored how to solve the detect capital problem by validating strings based on capitalization rules. Remember to optimize your solutions and handle edge cases carefully. Thanks for watching, and stay tuned for more problem-solving tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!